So this is our last part of the tutorial. So in this part what we will do is to verify that what we have reconstructed makes sense, and for that we have a number of tests that we can do, and those are not the only ones, and these are some of them, but with this low number of particles, these are the ones that makes more sense, and you can find them under analysis, 3D analysis, validation, and then you have here a number of tools. So the first one is this multi-reference alignability. So this one takes a set of particles, a set of a volume that it wants to compare it, and then the symmetry group, and the remaining normally you don't have to touch. Okay, so the output of this is a plot like this one. So in this plot we have two we are measuring two things here. So one is the angular precision, the other one is called angular accuracy, and the names may be very confusing and we never know which one is which, but those are measuring two features of the angular assignment. The first one is for every particle you have chosen one particular direction because it is the maximally correlating direction with the experimental image. But then you may wonder which is the second best correlating direction, which is the third best. And you would expect that for a good angular assignment they are all clustered around more or less the same direction. And if this is not the case, probably that is a particle for which you don't know where to put it, and then it is not you're not so sure about that angular assignment. The other one is all these algorithms, angular assignment algorithms, they start by making a global angular search, and then at some point they go into local angular searches, and it may be that they got trapped into local minima, and then if once you have converged you make a global angular assignment again, how likely it is that it receives an angle that is again close to the angle that you had in the previous reconstruction. If those two angles are close to each other, you are pretty close. You are more sure about the angular assignment, and if they are not close to each other, then you are uncertain about that angular assignment. And then we encode this as a number between 0 and 1, ideally. One of them is not bounded, so that is why we have this minus 400 or minus 500, whatever. So this is because just for one image this measure was terribly bad, but we can try to zoom in a region, so this region here between 0 and 1, and then one of them is not bounded. So but ideally you would like all the particles to be here in the 1, 1 region. So this is not exactly the case, but there are theoretical reasons to choose the ones that are below 0.5 in any one of those two numbers. So you may now sort by any one of them. So let's sort by this. We can look at what is the precision. So we would choose all these particles above 0.5, and that is what we'll do now. So you go to 0.5, that should be rather early. So they are here, and then up to this point you are not sure about the angular assignment, and the same for the accuracy. So again, you have the 0.5 that has some theoretical meaning, so we cannot see it because of these having some strange values, but they are sorted by 0.5 by accuracy, and then you may go to this point and say select to here, I don't trust these ones, and then you produce a new set of particles. That is what I did here. So those are the particles for which I'm completely sure about the angular assignment, and you may reconstruct again using a local refinement, and now you have lost a bit more of resolution. I think it was before 3, or I'm not sure about this. So this time is 3.3. In this case it was it was a bit better than 3.3. It was 3.2, but we are losing more and more particles in the process, and with this very low number of particles, well, that could be problematic. If we have many more particles, that is not that problematic. But keeping them there, even if the FSC is better, doesn't mean that you have a better reconstruction, because you know that the FSC rewards systematic errors. So if an image is systematically put in the wrong place, in terms of FSC, it doesn't matter. Actually, it is better to put them there, to put those images that are incorrectly assigned in that area. But it doesn't mean that you have a better structure. So let's look at the structure just to make sure that we have not spoiled it. So for instance, 97, that was the slice that we were looking before. So we don't see any artifacts around, we don't see this haze on top, and we knew from the beginning that this data set was limited to somewhere between 3 or 3.5 angstroms and 2.5 or 2 angstroms. So, but we see that the structure is pretty clean, and actually we can remove noise. It is volume. Oh, yeah. There is something to hide dust, but I don't know it by heart. But it is pretty. You see the alpha helices pretty well, and then we will clean it and restore it. For that we can use this deep E enhancer, and the deep E enhancer, let's look first at this branch. So this branch is looking at the resolution. So at this point you may define a mask, and this mask will help the directional resolution and the local resolution algorithms to concentrate on which area they should analyze. But it is not for masking, it is not for computing Fourier shell correlations. It is just to get rid of the noise, or to look at what is the distribution of the noise, and then you need where the noise region is. So this let's start with the local resolution. So the local resolution, the one of deep res, I find it quite accurate, and especially because Fourier shell correlation, the resolution that you report with the Fourier shell correlation can be understood as the best resolution that you have in the best voxel. And these local resolution measures, they tell you what is more the distribution of the resolution in your in your structure. So actually we don't have 3 angstrom or 3.2 angstrom resolution. Most of the voxels are more around 4, which is consistent with the fact that we have only we have less than 2,000 images. So we did a lot with 1,500 images. So it is not actually a negative thing, but with only 1,500 images, we already got a quite decent 3D structure. But trying to oversell our final result and say that we have a very high resolution when actually we don't have as high resolution is actually, I think it goes against our scientific credibility. Okay, so we have something that is a 4.2, let's say, which is a good, and also we can analyze the directional resolution. So so we can have a color, so the structure colored by resolution. So we have here something like this, let's say. So all these blue areas, they are more like 3 or 4 point something, and then some of the points, they are more they have a little better resolution, and only very few points they have such high resolution. But otherwise we don't have an absolutely great structure, and it's not expected to be so, because we didn't correct for the beam tilt, and we knew from the beginning it was to be limited by 3 angstroms resolution, and also we have only 1,500 images. We have done this in just one afternoon, so we cannot really have extremely high resolution with this data. Okay, good. But resolution is not only local, but it's also directional. So in different directions you have different resolutions, and one of the interesting things is to look how the interquartile range between different resolutions look like. So in the region of the structure, it is pretty consistent, so all inconsistencies come from the surrounding, but in the region of the structure we have some resolution consistency that is somewhere between 0.5 and 1 point something in angstroms. Sorry, I closed the wrong window. Another interesting plot is this one, where we have the resolution per direction. So this is for different directions, and we see how many voxels have their maximum resolution along that direction, and we see that it is not perfectly uniform, but it is pretty uniform, and also we can see it here. So here we have for some reason this didn't show well. Let me check again. Okay, so this is not showing for some reason. It may be a bug that we will fix in the next release. But this is the radial resolution. So the radial resolution is those are radial averages of the resolution in different directions, and the directions is highest resolution, so the best direction, the worst direction, and then the azimuthal direction, so and the radial direction. So radial is from the origin of the volume, so from the center of the volume outwards. Azimuthal is perpendicular to that, so it would be kind of plane that is perpendicular to the radial direction. And the beginning at the end of this plot is not significant for the apoferritin because it has very few voxels. So this is where the apoferritin starts appearing, and then at this point it starts disappearing. And the interesting part is the middle one, so the ones that are fully filled with apoferritin. So that is this central region, and we see that this is extremely flat, meaning that for all those areas, so the slope of this curve is related to the uncertainty of the angular assignment. So we have a very good angular assignment, and probably we are here limited by other factors that are not angular assignment. So we are limited by the CTF correction that we didn't use the beam tilt, and we are also limited by number of images, resolution of those images in the micrographs, and so on. So we see that the best direction, we have something, well, highest resolution is 1.4, but this is not something you can trust too much. So maybe in one direction we have this resolution, but this is not really the resolution overall in those voxels. And the worst resolution is 5. So there is and the average is somewhere here. So 3 is somewhere here. So we see that it is more or less consistent with the monoRes. So the monoRes is the one that gives more consistent estimates. So it is kind of deep res also, and it is more or less consistent with the FSC. So the FSC said something like 2 point something, 3 point something, and so this 2.8 is similar to that. And actually, if you look at the FSC, you see that the cross with 0.14 is around that 2.8. So 2.8 is here. This is a little bit better, 2.7. But just don't take these numbers as absolute numbers written in stone. So it gives you more or less a or a feeling of the quality of your map, but they shouldn't be taken as the absolute truth. Never, not only for XMIP, but for any one of the reconstructions. And then we can do some local deblurring. So that is considering the local resolution and then doing a 3D correction that is taking into account the local resolution to improve the volume. And the first one is the one that is fully supported by the theory, but then you can estimate again the local resolution of the second one, of the first refined or restored volume, and then refine it further and refine it further, and you could keep going. The problem with this approach is that the local resolution is less and less well defined if you use monoRes in these cases. So unless you use something like deep res, you can never be too sure about what it is. Okay, so let's look at the first one. But normally they look nice. So when you do several rounds of deblurring, they look very nicely. And here, for instance, here we see the alpha helices. They are pretty well defined. And this is if you deblur with the local resolution and following a Wiener restoration. We have recently introduced a new algorithm that we call it the deep EM enhancer. So the deep this algorithm learns from PDB structures how macromolecular features like alpha helices and side chains and beta sheets and so on look like, and then it takes this input and applies this previous knowledge, and the result is again also very clean. We can see it here, so you can see that it is really clean. And if we look at it in Chimera, if we look at it in Chimera, I don't like this one. I don't know what that one is showing. This one is better. You see that the alpha helices, they are absolutely greatly defined. You can see them here. Very nice background, very clean, and so on. So yeah, so this is our tutorial. The last step, this is just for fun. If you want, you can apply a further refinement or another restoration step using the local resolution estimated before. So you can estimate you can estimate the local resolution with deep res that doesn't look at the noise, and this deep res resolution here, it tells more. Before it was something more like 4. Now we have something like 2 point something, and then you can restore using that 2 point something and get an even better map. But this further refinement, at some point it may introduce some bias. So don't be too greedy on these kind of refinements. But on some features like these alpha helices have worked absolutely great with only 1500 images. And we have from the other branch of this angular assignment error validity, so we see that the directional is absolutely great. So this is sorry, I'm going in the wrong direction, but so this is a nice example that with good data you can reach very high resolution with a very short time. And one of the main messages I would like to convey here is that all this 3D structure determination is about determining what is a particle, what is not a particle. That is one of the parameters. The second parameter is whether this particle is really belonging to the 3D structure that I'm interested in. This is what you try to estimate with the 3D classification. And then once you have decided that it belongs to your structure, then you have to align that particle with respect to the structure. And those for that you need 3 angles and 2 shifts, or however you want to encode those parameters, but at least you need 5 numbers, and you have an extremely noisy environment in which you barely see anything in the particles. So all these numbers, they are subjected to very high noise. So when you have noise environment, you have noisy data, your estimate of parameters are also noisy. And unless you can combine different algorithms and make sure through all this consensus, we had a consensus for the defocus, we had a consensus for the particle picking, we had a consensus for the 2D classification, we had a consensus for the initial volume, for the 3D classification, for the angular assignment, and unless you employ all these consensus, you can never be sure that the parameters you have estimated are the correct ones. Because otherwise you are bound to believe that whatever single algorithms you are using, it is always making the right choice with absolutely no noise, and that is impossible. That doesn't exist. not even XME, but no other algorithm has no error. So unless you can be absolutely sure that what you are estimating is the right thing, you can never be absolutely sure about any fine detail of your 3D structure. And that would be all. I hope that you find Scipion useful, and if you have any problem, just write to us.